Johann Carl Friedrich Gauss, Latin, Carolus Fridericus Gauss, was a German mathematician who contributed significantly to many fields, including number theory, algebra, statistics, analysis, differential geometry, geodesy, geophysics, mechanics, electrostatics, astronomy, matrix theory, and optics. Sometimes referred to as the Princeps mathematicorum in greatest mathematician since antiquity. Gauss had an exceptional influence in many fields of mathematics and science and is ranked as one of history's most influential mathematicians. Early years. Carl Friedrich Gauss was born on 30 April 1777 in Brunswick, in the Duchy of Brunswick-Wolfenbüttel, as the son of poor working-class parents. His mother was illiterate and never recorded the date of his birth, remembering only that he had been born on a Wednesday, 8 days before the Feast of the Ascension, which itself occurs 39 days after Easter. Gauss later solved this puzzle about his birth date in the context of finding the date of Easter, deriving methods to compute the date in both past and future years. He was christened and confirmed in a church near the school he attended as a child. Gauss was a child prodigy. When he was 8, he figured out how to add up all the numbers from 1 to 100. There are also many other anecdotes about his precocity while a toddler, and he made his first groundbreaking mathematical discoveries while still a teenager. He completed Disquisitiones Arithmetici, his magnum opus, in 1798 at the age of 21, though it was not published until 1801. This work was fundamental in consolidating number theory as a discipline and has shaped the field to the present day. Gauss's intellectual abilities attracted the attention of the Duke of Brunswick, who sent him to the Collegium Carolinum, which he attended from 1792 to 1795, and to the University of Göttingen from 1795 to 1798. While at university, Gauss independently rediscovered several important theorems. His breakthrough occurred in 1796 when he showed that a regular polygon can be constructed by compass and straightedge if and only if the number of sides is the product of distinct Fermat primes and a power of 2. This was a major discovery in an important field of mathematics. Construction problems had occupied mathematicians since the days of the ancient Greeks, and the discovery ultimately led Gauss to choose mathematics instead of philology as a career. Gauss was so pleased by this result that he requested that a regular heptadecagon be inscribed on his tombstone. The stonemason declined, stating that the difficult construction would essentially look like a circle. The year 1796 was most productive for both Gauss and number theory. He discovered a construction of the heptadecagon on 30 March. He further advanced modular arithmetic, greatly simplifying manipulations in number theory. On 8 April he became the first to prove the quadratic reciprocity law. This remarkably general law allows mathematicians to determine the solvability of any quadratic equation in modular arithmetic. The prime number theorem, conjectured on 31 May, gives a good understanding of how the prime numbers are distributed among the integers. Gauss also discovered that every positive integer is representable as a sum of at most 3 triangular numbers on 10 July and then jotted down in his diary the note, epsilon upsilon rho eta kappa alpha. Num equals delta plus delta plus delta. On October 1 he published a result on the number of solutions of polynomials with coefficients in finite fields, which 150 years later led to the Weil conjectures. Middle years. Algebra in his 1799 doctorate in absentia. A new proof of the theorem that every integral rational algebraic function of one variable can be resolved into real factors of the first or second degree. Gauss proved the fundamental theorem of algebra, which states that every non-constant single-variable polynomial with complex coefficients has at least one complex root. Mathematicians, including Jean-Laurent D'Alembert, had produced false proofs before him, and Gauss's dissertation contains a critique of D'Alembert's work. Ironically, by today's standard, Gauss's own attempt is not acceptable, owing to implicit use of the Jordan curve theorem. However, he subsequently produced 3 other proofs, the last one in 1849 being generally rigorous. His attempts clarified the concept of complex numbers considerably along the way. Gauss also made important contributions to number theory with his 1801 book Disquisitiones Arithmetici, which, among other things, introduced the symbol for congruence and used it in a clean presentation of modular arithmetic, contained the first 2 proofs of the law of quadratic reciprocity, developed the theories of binary and ternary quadratic forms, stated the class number problem for them, and showed that a regular heptadecagon can be constructed with straight edge and compass. Astronomy. In that same year, Italian astronomer Giuseppe Piazzi discovered the dwarf planet Ceres. Piazzi could only track Ceres for somewhat more than a month, following it for 3 degrees across the night sky. Then it disappeared temporarily behind the glare of the sun. Several months later, when Ceres should have reappeared, Piazzi could not locate it. The mathematical tools of the time were not able to extrapolate a position from such a scant amount of data. 3 degrees represent less than 1% of the total orbit. Gauss, who was 24 at the time, heard about the problem and tackled it. After 3 months of intense work, he predicted a position for Ceres in December 1801, just about a year after its first sighting, and this turned out to be accurate within a half degree. When it was rediscovered by Franz Xaver von Zach on 31 December at Gotha, and 1 day later by Heinrich Olbers in Bremen, Gauss's method involved determining a conic section in space. Given one focus and the conic's intersection with 3 given lines and given the time it takes the planet to traverse the arcs determined by these lines, this problem leads to an equation of the 8th degree, of which one solution, the Earth's orbit, is known. The solution sought is then separated from the remaining 6 based on physical conditions. In this work, Gauss used comprehensive approximation methods which he created for that purpose. One such method was the fast Fourier transform. While this method is traditionally attributed to a 1965 paper by J. W. Cooley and J. W. Tukey, Gauss developed it as a trigonometric interpolation method. His paper, Theoria Interpolationis Methoda Nova Tractata, was only published posthumously in Volume 3 of his collected works. This paper predates the first presentation by Joseph Fourier on the subject in 1807. Zach noted that, without the intelligent work and calculations of Dr. Gauss, we might not have found Ceres again. Though Gauss had up to that point been financially supported by his stipend from the Duke, he doubted the security of this arrangement, and also did not believe pure mathematics to be important enough to deserve support. Thus he sought a position in astronomy, and in 1807 was appointed professor of astronomy and director of the Astronomical Observatory in Göttingen, a post he held for the remainder of his life. The discovery of Ceres led Gauss to his work on a theory of the motion of planetoids disturbed by large planets, eventually published in 1809 as Theoria Motus Corporum Coelestium in Sectionibus Conicis Solum Ambientum. In the process, he so streamlined the cumbersome mathematics of 18th-century orbital prediction that his work remains a cornerstone of astronomical computation. It introduced the Gaussian gravitational constant, and contained an influential treatment of the method of least squares, a procedure used in all sciences to this day to minimize the impact of measurement error. Gauss proved the method under the assumption of normally distributed errors. The method had been described earlier by Adrien Marie Legendre in 1805, but Gauss claimed that he had been using it since 1795. Geodesic survey in 1818. Gauss, putting his calculation skills to practical use, carried out a geodesic survey of the Kingdom of Hanover, linking up with previous Danish surveys. To aid the survey, Gauss invented the heliotrope, an instrument that uses a mirror to reflect sunlight over great distances, to measure positions. Non-Euclidean geometries. Gauss also claimed to have discovered the possibility of non-Euclidean geometries but never published it. This discovery was a major paradigm shift in mathematics, as it freed mathematicians from the mistaken belief that Euclid's axioms were the only way to make geometry consistent and non-contradictory. Research on these geometries led to, among other things, Einstein's theory of general relativity, which describes the universe as non-Euclidean. His friend Farkas Wolfgang Bolyai, with whom Gauss had sworn brotherhood and the banner of truth as a student, had tried in vain for many years to prove the parallel postulate from Euclid's other axioms of geometry. Bolyai's son, János Bolyai, discovered non-Euclidean geometry in 1829. His work was published in 1832. After seeing it, Gauss wrote to Farkas Bolyai, "To praise it would amount to praising myself, for the entire content of the work coincides almost exactly with my own meditations, which have occupied my mind for the past 30 or 35 years. This unproved statement put a strain on his relationship with János Bolyai, but it is now generally taken at face value. Letters from Gauss years before 1829 reveal him obscurely discussing the problem of parallel lines. Waldo Dunnington, a biographer of Gauss, argues in Gauss, Titan of Science, that Gauss was in fact in full possession of non-Euclidean geometry long before it was published by János Bolyai, but that he refused to publish any of it because of his fear of controversy. Theorem or egregium. The geodetic survey of Hanover, which required Gauss to spend summers traveling on horseback for a decade, fueled Gauss's interest in differential geometry and topology, fields of mathematics dealing with curves and surfaces. Among other things, he came up with the notion of Gaussian curvature. This led in 1828 to an important theorem, the theorem or egregium, establishing an important property of the notion of curvature. Informally, the theorem says that the curvature of a surface can be determined entirely by measuring angles and distances on the surface. That is, curvature does not depend on how the surface might be embedded in three-dimensional space or two-dimensional space. In 1821, he was made a foreign member of the Royal Swedish Academy of Sciences. Later years and death. In 1831, Gauss developed a fruitful collaboration with the physics professor Wilhelm Weber, leading to new knowledge in magnetism and the discovery of Kirchhoff's circuit laws in electricity. It was during this time that he formulated his namesake law. They constructed the first electromechanical telegraph in 1833, which connected the observatory with the Institute for Physics in Göttingen. Gauss ordered a magnetic observatory to be built in the garden of the observatory, and with Weber founded the Magnetische Verein, which supported measurements of Earth's magnetic field in many regions of the world. He developed a method of measuring the horizontal intensity of the magnetic field which was in use well into the second half of the 20th century, and worked out the mathematical theory for separating the inner and outer sources of Earth's magnetic field. In 1840, Gauss published his influential Dioptrische Untersuchungen, in which he gave the first systematic analysis on the formation of images under a paraxial approximation. Among his results, Gauss showed that under a paraxial approximation, an optical system can be characterized by its cardinal points, and he derived the Gaussian Len formula. In 1845 he became associated member of the Royal Institute of the Netherlands. When that became the Royal Netherlands Academy of Arts and Sciences in 1851, he joined as foreign member. In 1854, Gauss selected the topic for Bernhard Riemann's Habilitation-Vortrag über die Hypothesen, welche der Geometrie zugrunde liegen. On the way home from Riemann's lecture, Weber reported that Gauss was full of praise and excitement. Gauss died in Göttingen, in the Kingdom of Hanover on 23 February 1855 and is interred in the Albani Friedhof Cemetery there. Two individuals gave eulogies at his funeral. Gauss's son-in-law Heinrich Ewald and Wolfgang Sartorius von Waltershausen, who was Gauss's close friend and biographer. His brain was preserved and was studied by Rudolf Wagner, who found its mass to be 1,492 grams and the cerebral area equal to 219,588 square millimeters. Highly developed convolutions were also found, which in the early 20th century was suggested as the explanation of his genius. Religious views. Gauss was a Lutheran Protestant, a member of the St. Albans Evangelical Lutheran Church in Göttingen. Potential evidence that Gauss believed in God's grace comes from his response after solving a problem that had previously stumped him. Finally, 2 days ago, I succeeded, not on account of my hard efforts, but by the grace of the Lord. One of his biographers, G. Waldo Dunnington, describes Gauss's religious views in these terms. For him science was the means of exposing the immortal nucleus of the human soul. In the days of his full strength it furnished him recreation and, by the prospects which it opened up to him, gave consolation. Toward the end of his life it brought him confidence. Gauss' God was not a cold and distant figment of metaphysics, nor a distorted caricature of embittered theology. To man is not vouchsafed that fullness of knowledge which would warrant his arrogantly holding that his blurred vision is the full light and that there can be none other which might report truth as does his. For Gauss, not he who mumbles his creed, but he who lives it, is accepted. He believed that a life worthily spent here on earth is the best, the only, preparation for heaven. Religion is not a question of literature, but of life. God's revelation is continuous, not contained in tablets of stone or sacred parchment. A book is inspired when it inspires. The unshakable idea of personal continuance after death, the firm belief in a last regulator of things, in an eternal, just, omniscient, omnipotent God, formed the basis of his religious life, which harmonized completely with his scientific research. Apart from his correspondence, there are not many known details about Gauss' personal creed. Many biographers of Gauss disagree with his religious stance, with Bühler and others considering him a deist with very unorthodox views, while Dunnington points out that he was, at least, a nominal Lutheran. In connection to this, there's a record of a conversation between Rudolf Wagner and Gauss, in which they discussed William Whewell's book of the plurality of worlds. In this work, Whewell had discarded the possibility of existing life in other planets, on the basis of theological arguments. But this was a position with which both Wagner and Gauss disagreed. Later Wagner explained that he did not fully believe in the Bible, though he confessed that he envied those who were able to easily believe. This later led them to discuss the topic of faith, and in some other religious remarks, Gauss said that he had been more influenced by theologians like Lutheran minister Paul Gerhardt than by Moses. Other religious influences included Wilhelm Braubach, Johann Peter Sussmilch, and the New Testament. Dunnington further elaborates on Gauss's religious views by writing, Gauss' religious consciousness was based on an insatiable thirst for truth and a deep feeling of justice extending to intellectual as well as material goods. He conceived spiritual life in the whole universe as a great system of law penetrated by eternal truth, and from this source he gained the firm confidence that death does not end all. Gauss declared he firmly believed in the afterlife, and saw spirituality as something essentially important for human beings. He was quoted stating, "The world would be nonsense. the whole creation an absurdity without immortality, and for this statement he was severely criticized by the atheist Eugen Dühring, who judged him as a narrow, superstitious man. Though he was not a churchgoer, Gauss strongly upheld religious tolerance, believing that one is not justified in disturbing another's religious belief, in which they find consolation for earthly sorrows in time of trouble. When his son Eugene announced that he wanted to become a Christian missionary, Gauss approved of this, saying that regardless of the problems within religious organizations, missionary work was a highly honorable task. Family. Gauss's personal life was overshadowed by the early death of his first wife, Johanna Osthoff, in 1809, soon followed by the death of one child, Louis. Gauss plunged into a depression from which he never fully recovered. He married again, to Johanna's best friend named Friederike Wilhelmina Waldeck, but commonly known as Minna. When his second wife died in 1831 after a long illness, one of his daughters, Therese, took over the household and cared for Gauss until the end of his life. His mother lived in his house from 1817 until her death in 1839. Gauss had 6 children. With Johanna, his children were Joseph, Wilhelmina and Louis. With Minna Waldeck he also had 3 children, Eugene, Wilhelm and Therese. Eugene shared a good measure of Gauss's talent in languages and computation. Therese kept house for Gauss until his death, after which she married. Gauss eventually had conflicts with his sons. He did not want any of his sons to enter mathematics or science for fear of lowering the family name, as he believed none of them would surpass his own achievements. Gauss wanted Eugene to become a lawyer, but Eugene wanted to study languages. They had an argument over a party Eugene held, which Gauss refused to pay for. The son left in anger and, in about 1832, emigrated to the United States, where he was quite successful. While working for the American Fur Company in the Midwest, he learned the Sioux language. Later he moved to Missouri and became a successful businessman. Wilhelm also moved to America in 1837, and settled in Missouri, starting as a farmer and later becoming wealthy in the shoe business in St. Louis. It took many years for Eugene's success to counteract his reputation among Gauss's friends and colleagues. See also the letter from Robert Gauss to Felix Klein on 3 September 1912.